The sun goes down, the stars come out. Where the times go, my universe will never be the same.
Pop Danthology.
To be a successful college kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics. What actually happens when you kick the ball, and why is the ball go where you ask it to go? The answer lies in the Newton's second law of motion. Newton's second law basically says force equals mass times acceleration, and what that means is the force is proportional to the acceleration if the mass remains the same. The second law is one of the three laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move. So, if you have an object with a mass that is accelerating, and accelerating means a change in velocity. That change in velocity is equal to the amount of force applied to the object. The way to say it with words is force is equal to mass times acceleration. The word velocity means a quickness in speed or motion. So, if you increase the force on something, it will accelerate more rapidly. An acceleration is either speeding up, slowing down, or changing direction. So, a rapid acceleration will give us a change in speed very quickly, and the mass of a football, of course, stays the same. So, you kick the football harder, it's going to accelerate more rapidly. Now, what happens is this. Football only accelerates or speeds up as long as your foot is in contact with the football applying the force. The entire process happens in less than 1.5 from snap to hold to kick. Most kickers take a three-step approach to the ball. The final step is the plant foot, which provides a stable platform for the kick. The kick itself involves the entire leg building the force necessary to launch the football. A kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. As long as your foot remains in contact with the ball applying the force, you can make the football speed up. When his foot breaks his contact with the ball begins to slow down, because gravity and air friction will make it to slow down. So when you kick a football, your foot applies a force the ball, sending it off to a high rate of speed, hopefully way down the field or through the goalpost.
Good morning and good night. I wake up at twilight. Starships were meant to fly.
We don't even have to try. Oppan Gangnam Style.
And it feels like I am just too close to love you.
Ball games are played with balls, right? Footballs, tennis balls, basketballs, golf balls, cricket balls. There's one thing they have all in common. They're round, most definitely circular, positively spherical. So, ever wonder rugby balls are egg-shaped, unlike those used in other sports? So, why the oval shape? In the early days, balls were made using inflated pig's bladders, and so took on a similar shape. Really? They were made more of a plump shape to begin with? much larger and rounder than they are today. Some people believe the more elongated shape developed because it was more suited to a game like rugby that involved running with the ball as well as kicking it. So we talked about wide oval shape, but what was wrong with the old shaped balls? Okay. The problem with having old shaped balls, by which of course I mean the rugby balls. Well, to be precise, a rugby ball is a prolate ellipsoid that is something that is like a 3D version of an ellipse, but having a cross section along its long axis of a circle. Rugby balls behave awkwardly. In one sense, that's obvious. Their awkward shape will lead to awkward movement. On the ground at least. But what about when in the air? Why is it hard to get a rugby ball to spin nicely and stay in one orientation? Or put another way, why is it so easy to make a rugby ball tumble all over the place in flight, making it more difficult for the opposing fullback to catch? Once in the air, the rugby ball undergoes torque-free movement. That means there's no external force trying to create extra spin on the ball. The behavior of an object in this situation can be described by Euler's equations. I don't really want to talk about those equations because they are not that difficult to interpret if you know about the rotational inertia and angular velocities. And this equation can be solved very simply in some cases. It turns out that if you have a rugby ball that is spinning on its long axis, the rotation is stable. That means once you have established it's rotating in this manner, it will remain doing so. If the ball is perturbed slightly of the spin, it will return to this direction. However, the same is not true if you spin the ball about the short axis. In this case, the motion is critically stable, meaning that any perturbation is not corrected. The ball can easily lose this manner of motion and start moving in another way. If you don't start it exactly in this way of movement, it's unlikely to stay there. Find yourself a rugby ball and try it. Perhaps more interesting is the case when you have an object with three axes of different lengths, like a paper book. You'll find that if you try to spin the book about its long axis or its short axis, these are stable, but about the middle axis, the rotation is unstable. Try it. Take a book, a cuboid with three different length axes, hold it with its cover the right way up and facing you, and grip its bottom two corners. Now flip it in the air, try to get it to spin 360 degrees and catch it again by its bottom two corners. See what happens. It's very difficult to do. The book will tumble around because rotation about this middle axis is not stable. Any small perturbation from it will be magnified as the book spins. However, you try the same experience spinning about one of the other axes of the book, and you find the motion stable. Incidentally, if you take an object with three identical axes, like a soccer ball, its rotations are critically stable in all directions, which is one reason why a soccer ball in flight can spin and bend in all kinds of wacky ways. Thank you.